In this video, we'll be discussing integrals of trigonometric functions from 0 to 2 pi. So these integrals differ from the ones we've done before, mostly in their limits. So here's an example. This is the example we'll be working out in this video to show how it's done, but in general, they look like this. It's the integral from 0 to 2 pi, and so the bounds are always from 0 to 2 pi, of r of cosine theta and sine theta. So this r is a rational function of sine theta and cosine theta. So it's just some numerator over denominator, and both the numerator and the denominator are some function of cosine or sine. So here's an example. We have d theta over 2 plus cosine theta. So this is indeed a rational function of cosine and sine. There's no sine in here, but we have cosine in the denominator, and the numerator would just be 1. So technically it's a function itself. It doesn't have any cosines or sines, but these functions are generally classified by having cosines and sines and some other combination of numbers in the numerator and denominator. Okay, so let's just see how we solve this. So this whole video will just be solving this example, and it'll kind of lay the groundwork for how to solve these problems in general. So the first step is going to be a substitution. We want to say z equals e to the I theta. So we're going to define a new variable z, and we're going to define it as e to the I theta, where theta is the variable that's already here. Now we want to take the derivative. dz d theta equals I e to the I theta equals iz, because e to the I theta is z, remember? So we have iz. Now we isolate for d theta. We have d theta equals dz over iz, and furthermore we want to try to find cosine theta, which is one part. If this had a sine theta in it, we would also want to find sine theta, but since it's just cosine, we'll just stick with this. Cosine theta from, remember the trigonometric video at the very beginning, this equals e to the I theta plus e to the negative I theta over 2. And e to the I theta is what? It's z, and e to the negative I theta would be 1 over z, so it's going to be z plus 1 over z over 2. Now we have all the parts in place to transform this into an integral from that involves theta into an integral that involves our new variable z. So this is the integral that was written that we're trying to solve, and we're going to transform this. So it's going to be integral of, and d theta we said was dz over iz, so we have dz over iz, and we have 2 plus cosine theta in the denominator, so we're going to have 2 plus and this expression for cosine theta that we found, so 2 plus that expression, and then we have a 1 in the numerator, like that. So the next thing we would do is try to figure out how the limits change. So how did the limits change? They used to be from 0 to 2 pi. So as theta goes from 0 to 2 pi, what happens to z? So we recognize this right here as the equation of a circle. This is a circle with radius 1, centered at 0. And as we go from 0 to 2 pi, we go around the whole circle in a counterclockwise direction. So really, this is just the integral over that circle, over the unit circle in the counterclockwise or positive-oriented direction. So we just say that's the integral over modulus z equals 1, which is another way of saying it's the integral over that unit circle in the counterclockwise direction. Okay, so now that we have put it in terms of z, we can go ahead and try to solve it using residue theorem. So we're going to go ahead down here and see that this equals, we're going to try to clean this up a little bit because these integrals can get kind of messy, so you want to keep cleaning them up so you don't get distracted or confused as you're solving it. So we clean up the denominator, and we're going to get the 2 in the denominator here will come up to the numerator, the reciprocal, and we'll get 2 over 4 plus z plus 1 over z, and we have again dz over iz, and then we have over the circle modulus z equals 1. Now we see that this is I is in the denominator. We have 1 over I, and 1 over I is negative I. So easy way to see that, 1 over I, and then you multiply both the top and bottom by I, you get I over negative 1, which is just negative I. Okay, so we take the negative I outside because it's a constant, and we're left with 2 over, and what I did down here is I multiplied this z over here with this expression right here, and we got 4z plus z squared plus 1. Okay, so we have something that looks a lot cleaner. We have this integral right here. So the next thing we're going to do, we're going to define that function right here, that integrand, as f of z. We're going to say f of z equals 2 over z squared plus 4z plus 1. And the next thing we want to do is find where that has isolated singularities. And in this case, they're going to be poles, because it's only going to be when the denominator is going to be 0. So we need to find when the denominator is 0, because that's going to be where the isolated singularities are. And since it's a quadratic, we can just use quadratic formula, and we get z equals negative 2 plus rad 3 or negative 2 minus rad 3. And so again, we don't need to consider both of these. In fact, if we do, we'll get the wrong answer. We only need to consider the one that's inside our contour. So what's our curve or contour in this example? Our curve is going to be our curve is going to be modulus z equals 1, or that unit circle that I've drawn right here. Now, which of these, if any, lie inside that curve? So negative 2 minus rad 3 is about 1.7, so this is about negative 3.7, so it's all the way over here. It does not lie inside our circle. Negative 2 plus rad 3, so negative 2 plus about 1.7 is about negative 0.3, so it fits the description. it lies inside our circle. So we only need to consider this one. We should not and will not consider that one right there. So we're only going to consider this one for the residue theorem. Okay, so the integral, the answer to our problem would be, or the answer to this new problem, we're just worrying about this integral right now. We'll tag on the negative I at the very end. So this integral right here would be equal to 2 pi I times the residue of f of z at negative 2 plus rad 3, because that's the only one that lies inside our curve. Okay, so then we have f of z is this again, and now we need to separate a of z and b of z. A of z is going to be the numerator, and b of z will be the denominator. So again, for the denominator, we want to pick the denominator so that it's going to be 0, and only it will be 0. So the motivation behind picking this in this green box as our a of z, and the purple box right here as our b of z, is that we want to put this in a form of the poles. Remember, the poles were in the form of h of z over z minus z naught to some power m, and that equals f of z. Poles were in that form, and h of z was analytic on our domain, and this was z minus z naught to the power of something. So that's why I have this denominator, b of z, is z minus, this is going to be our z naught to the power of something. In this case, it's nice, to the power of 1. And our numerator, this whole thing is analytic inside our in our curve, because our curve is this, and the only reason this numerator wouldn't be analytic is if we put in negative 2 minus rad 3, but we can't put that in because that's all the way out here. So inside this curve, everything is fine for the numerator. So the next thing we would do is find the residue that we're looking for. We're trying to find the residue of f of z at negative 2 plus rad 3. And again, we've done this once or twice already. When you have it in this form where the numerator is analytic inside your curve and the denominator is equal to 0. So b of z naught indeed equals 0, but b prime of z naught is not equal to 0. So because of those, we can use the formula. We can do a of z naught over b prime of z naught, and z naught in this case is negative 2 plus rad 3. So a of z naught is going to be this big expression right here, and b of z naught, well, if we take b prime of z naught is going to be just 1, so there's nothing to plug in, it's just 1. And now we can clean this up. So this is going to come out to 1 over radical 3. And again, we need to multiply that by 2 pi I to get the integral, so we would have 2 pi I times 1 over rad 3. Now be careful, you're not done yet, because the integral you just found is this integral right here, underlined in red. We need to multiply that by negative I in order to get the original integral's answer, this one that we wanted. So take this and multiply it by negative I, and once you do that, you'll get I and I squared is negative 1, and we have a negative here, so that all cancels, and we're just left with 2 pi over radical 3. And that's the answer. And the answer is a real value. There's no imaginary part here. Is that what we expected? Well, let's look at the original integral. In fact, this is a real integral, because there's no i's anywhere here. It's just d theta over 2 plus cosine theta, 0 to 2 pi. So the limits are real. This integrand is real, so we expect a real answer. So if you get an imaginary answer, you probably did something wrong. You want to go back and check that again.